Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be discussing equilibrium, and in this chapter we're going to cover the following objectives. In the first objective, we're going to learn about the difference between reversible versus irreversible reactions. In this chapter, we will focus on reversible reactions and then begin to discuss chemical equilibrium. For that, we're going to need to define, understand, and learn to calculate the equilibrium constant expression for a reaction. Finally, we will discuss how to determine the sign for change in Gibbs free energy and the direction of a reaction given the equilibrium constant. Then the second objective is titled gas phase. Here we're going to cover how the equilibrium constant for gas phase equilibrium is expressed in terms of partial pressures of each gas. Then we'll move into the third objective, where we will learn to use Le Chatelier's principle to determine how changing conditions like temperature, pressure, and concentration changes will affect a reaction previously in equilibrium. Finally, our last objective is titled kinetic and thermodynamic control. In this final objective, we will identify the conditions that will cause a reaction to favor the kinetic or the thermodynamic product. In addition, we will cover how to distinguish between a kinetic and a thermodynamic pathway on a reaction coordinate diagram. To begin this chapter, I want to remind you the distinction between kinetics, which we covered last chapter, and equilibrium. Kinetics and equilibrium are two fundamental concepts in chemical reactions that, while related, describe different aspects of a system. Kinetics is the study of reaction rates, which involves the speed at which a reaction proceeds. It is concerned with the journey of a chemical reaction from reactants to products. Factors that affect the rate of a reaction include the concentrations of reactants, temperature, and the presence of a catalyst. On the other hand, equilibrium is concerned with the destination of a reaction. It describes the state at which the concentrations of reactants and products have become constant due to the forward and reverse reactions proceeding at the same rate. At this point, the system is said to be at equilibrium. So while kinetics tells us how fast a reaction will occur, equilibrium gives us information on the extent of the reaction, or how much of the reactants will be transformed into products when the reaction is complete. With that, we can officially begin this chapter. Chemistry fundamentally explores how substances interact and transform into new substances. This transformation involves reactants, which are the substances that enter a reaction, turning into products, which are the new substances produced by the reaction. Most chemical studies will focus on understanding the nature of these transformations, which can vary greatly in their behavior and in their outcomes. Chemical reactions can broadly be classified into two categories based on their directionality. The first category is irreversible reactions. These reactions proceed in one direction. Once the reactants are converted into products, the reaction stops because the products do not readily convert back into the original reactants. An example is the combustion of gasoline, which releases energy in gases that do not easily reform into gasoline. The second category is reversible reactions. Reversible reactions do not proceed to completion. The products formed can react among themselves to regenerate the original reactants, and this back and forth process can occur indefinitely. Now, in this chapter, we're going to focus on reversible reactions. And within the context of reversible reactions, chemical equilibrium represents a state where the rate of the forward reaction equals the rate of the reverse reaction. In other words, the rate for the reactants converting to products equals the rate of the products converting back to reactants. This balance results in the concentration of both reactants and products remaining constant over time. Now, it's crucial to understand that at equilibrium, the reaction has not stopped. It just continues to occur in both directions at equal rates. And this dynamic equilibrium is a key concept in understanding how chemical reactions can be influenced and controlled. To quantitatively analyze a chemical equilibrium, we use a crucial tool called the equilibrium constant, which is denoted as K. Let's consider a generic chemical reaction where A moles of reactant A and B moles of reactant B react together to give us C moles of product C and D moles of product D. The balanced chemical equation for this reaction can be represented in this way. The lowercase letters A, B, C, D, they represent the stoichiometric coefficients in the reaction, indicating the proportions in which the reactants and products participate in the reaction. Now, the equilibrium constant expression for this reaction, which helps us understand the extent of the reaction at equilibrium, is given by this expression right here. What we see is that in the numerator, we have the concentration of the products raised to their stoichiometric coefficients, and that is divided by the concentration of the reactants raised to their stoichiometric coefficients. The equilibrium constant K is then calculated as a ratio. And this formula shows us how the concentration of reactants and products at equilibrium affect the progress and extent of the reaction. Now, the next thing we want to discuss is the law of mass action. The law of mass action provides the foundation for the equilibrium constant expression. The law of mass action states that at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And this principle allows us to write the rate expressions for both the forward and reverse reactions in terms of the concentrations of the reactants and products raised to the power of their stoichiometric coefficients. The law of mass action essentially provides a bridge between the concepts of kinetics and equilibrium. It allows us to understand the rate at which reactions occur and the proportions of reactants and products present at equilibrium. It also allows us to predict the direction a reaction will proceed to reach equilibrium when conditions such as concentration, pressure, or temperature change. Now, because of the law of mass action, for our generic reaction, we can write the rate of the forward reaction, and we can write the rate of the reverse reaction. At equilibrium, the rates of the forward and reverse reactions are equal, and that allows us to write the following expression you see here. If we rearrange this equation, it'll give us the equilibrium constant expression. We can write the ratio between the rate of the forward reaction over the rate of the reverse reaction, which gives us the concentration of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. And this gives us the equilibrium constant expression. Now, if you remember the last chapter, we said for rate laws, the exponents are determined experimentally. Why is it here that we wrote the rate laws for the forward and reverse reactions using the coefficients from the balanced reaction? Again, this is a consequence of how we defined the law of mass action. Think of it this way. When a chemical reaction reaches equilibrium, the rate at which reactants turn into products is the same as the rate at which products turn back into reactants. The equilibrium constant K tells us about this balance. It uses the stoichiometric coefficients because these coefficients represent the actual proportions of molecules reacting with each other. Now, another important point I want to make here is the following. When we're studying chemical equilibrium, we might encounter different notations for the equilibrium constant, such as KEQ or KC. Although they are related, each has its specific context and application. KEQ, this is the general equilibrium constant for any reaction at equilibrium. Kc, this is the equilibrium constant specifically in terms of molar concentrations used for reactions in solution. Therefore, Keq is a broader term that can be used in any context where an equilibrium constant is relevant, while Kc is specifically used for solutions where concentrations in molarity are measured. You might also see Kp. This is the equilibrium constant in terms of partial pressures. This is used for gaseous reactions, and we're actually going to cover this in the second objective. Then in later chapters in this general chemistry course, we're going to be introduced to Ksp, Ka, and Kb. So just keep that in mind as we work through this chapter and the following chapters as well. Now, another thing that's important for us to learn is how to calculate equilibrium concentrations. And this is best taught using a guided example problem, so that's exactly what we're going to do. Let's go ahead and read this problem. This problem states, suppose a 250 milliliter flask is filled with 1.4 moles of oxygen gas and 1.9 moles of nitrogen monoxide. The following reaction becomes possible. 1 mole of nitrogen gas reacts with 1 mole of oxygen gas to give us 2 moles of nitrogen monoxide. Now, the equilibrium constant K for this reaction is 2.91 at the temperature of the flask. Calculate the equilibrium molarity of oxygen gas and round your answer to 2 decimal places. Now, first, we want to start by discussing what this question stem is asking of us and come up with a game plan before we attempt to solve. We're given the equilibrium constant, we're given some information about the initial quantities of the reactants and products, and we are asked to calculate the equilibrium molarity of oxygen gas. With this information, we want to initially write up our expression for the equilibrium constant. We aren't trying to calculate K here, we're given that value. Instead, we want to set this expression up and work backward from there to accomplish our actual goal, which is figuring out the equilibrium molarity of oxygen gas. But we can't plug in values into that expression because we know what we're starting off with in terms of reactants and products, but we do not know the actual equilibrium values. In order to do that appropriately, we're going to be taking advantage of a strategy called the ICE table. ICE is an acronym standing for initial, change, and equilibrium. Let's go ahead and set up an ICE table for our given problem to better understand this. Again, we want to write initial, change, and equilibrium on the sides here, and then we have our species that we're dealing with in our chemical reaction. Now, the first thing we want to do in this initial row is write our concentrations for each of our species. Now, for oxygen, we're given the moles we're starting off with, 1.4 moles of oxygen, and we know the volume of the flask, 250 milliliters, which is equal to 0.250 liters. This gives us our concentration for oxygen gas, and it is equal to 5.6. We want to do the same thing with nitrogen monoxide. We know we have 1.9 moles, and we have our volume of the flask, which is 250 milliliters. Again, that's 0.250 liters. And this gives us a concentration for nitrogen monoxide that is equal to 7.6. Now, what about the concentration for nitrogen gas? Since there's no mention of moles of nitrogen gas, we can assume its initial concentration is 0. Now, for the change row, we represent the changes in concentration with the variable x. Since we're determining the equilibrium position from an initial state where nitrogen monoxide is present, but nitrogen gas is not, the reaction is going to move in the reverse direction to produce nitrogen gas and consume nitrogen monoxide until equilibrium is reached. So for this reaction, we are going to be consuming nitrogen monoxide and we are going to be forming nitrogen gas and as a consequence, oxygen gas as well. Now for every mole of nitrogen gas formed, 1 mole of oxygen gas is also formed. There's a 1-to-1 ratio here. For every mole of nitrogen and oxygen gas formed, 2 moles of nitrogen monoxide are consumed. And so for this reason, the changes will be plus X for nitrogen and oxygen gas and minus 2X for nitrogen monoxide. Now our final row is our equilibrium row. The final row will be the initial concentration plus or minus the change, and that gives us the equilibrium concentrations. So for nitrogen gas, that's going to be X. For oxygen gas, that's going to be 5.6 plus X. And for nitrogen monoxide, that is going to be 7.6 minus 2X. Now we can set up our equilibrium constant. We know that the equilibrium constant is defined as the concentration of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. And we're told in the problem that the equilibrium constant is equal to 2.91. So what we can do now is replace these concentration terms with what we determined from our equilibrium row in our ICE table. So nitrogen monoxide, the concentration is replaced with 7.6 minus 2X. Our concentration for nitrogen gas is replaced with X, and our concentration for oxygen gas is 5.6 plus X. Now at this point, I want to pause and I want to discuss something called the 5% approximation rule. In some problems, we can simplify our calculations by making the assumption that the change in concentration of a reactant or product is negligible compared to the initial concentration. This rule is usually known as the 5% approximation rule, and this is a guideline that helps us determine when it is reasonable to make the simplification assumption. This rule states that if the change in concentration X is less than 5% of our initial concentrations, then X is negligible. This is often valid when K is very small or very large, or when the initial concentration is significantly high. However, in cases where K, our equilibrium constant, is of comparable magnitude to the initial concentrations, or when we don't have a huge excess of reactants, we have to solve the problem without this assumption. Now, looking at the value of K that we have and our concentrations, the values are pretty similar. So for this problem, we cannot make this assumption. Now, as a side note as well, if you do not know when to make this assumption, a safe bet 100% of the time is not to attempt to make any assumption at all and solve it the way that we're going to do for this problem. So no approximation rule here. Let's go ahead and begin to solve this. So what we have for our equilibrium expression is that 7.6 minus 2x squared divided by x multiplied by 5.6 plus x is equal to 2.91. And we want to go ahead and solve for x. The first step we want to do is we want to clear the fraction. We want to clear the fraction by multiplying both sides by the denominator. This is what we get when we do that. Second, we want to expand and multiply out both sides so that we no longer have these parentheses. When we do that, we get the following expression. In our third step, we're going to collect all terms to one side and add and subtract out like terms. When we do that, we get the following expression. The form that we have now is the general form of a quadratic equation, which is ax squared plus bx plus c is equal to 0. Since we have this general form of a quadratic equation, we can solve for x using the quadratic formula. The quadratic formula is used to find the values of x that satisfy a quadratic equation of this form. X is equal to the negative of b plus or minus square root of b squared minus 4ac divided by 2a. So again, we're going to use the quadratic formula. This is the form of the quadratic formula. It's going to help us find the values of x that satisfy this quadratic equation. Now here, our value for a is 1.9. Our value for b is negative 46.696. And our value for c is 57.76. So we take those values of a, b, and c, we plug them into our quadratic formula to get the following expression. And then we can plug this into a calculator to get the possible value or values for x. By applying the quadratic formula, we find two possible values for x. X can be 41.5655, or x can be 1.2749. The question now becomes, which one of these answers is correct? Let's go ahead and take both values and plug them back into our ICE table to see if we can figure out the answer. If x is equal to 41.5655, and we use that value to plug back into our ICE table, specifically our equilibrium row, we get the following concentrations. And what we notice here is that the concentration for nitrogen monoxide is negative. That doesn't make any sense. Negative molarity, that's not practical. Therefore, we can go ahead and eliminate this choice for that reason. Let's try to plug in our other x value. X equals 1.2749. If we use this value of x and we plug back into our equilibrium row, we get the following concentration for nitrogen gas, for oxygen gas, and for nitrogen monoxide. These concentrations make sense. We don't get any unusual numbers and we don't get any negative molarities. This is the correct answer for x, and these are our equilibrium concentrations. Now we're asked specifically for the equilibrium concentration of oxygen gas, rounded to 2 decimal places, and that answer is going to be 6.87. And with that, we've solved this problem. Now I want to tackle another one just to make sure we really understand all of these concepts. This problem says, what are the concentrations of a 0.15 molar solution of hydrogen cyanide? And here we're given the reaction. Hydrogen cyanide decomposes into hydrogen cations and cyanide anions. And the equilibrium constant for this reaction is 4.9 times 10 to the negative 10. Now, to solve this problem, we're going to follow the same protocol we did for the previous problem. First, we're going to set up an expression for the equilibrium constant. Not to solve for k, we're already given that, but instead to work backwards to calculate the equilibrium molarities. In order to do that, we need to set up an ICE table to figure out our equilibrium values. Now, just as a reminder, an ICE table is an organized way to approach problems involving equilibrium. It allows us to track the concentrations of reactants and products at 3 stages: the initial concentration, the change that occurs as the system reaches equilibrium, and finally, the equilibrium concentration. Now, for the initial row here, we're only given the concentration for hydrogen cyanide. It's equal to 0.15. That means that the initial concentration for the hydrogen cations and the cyanide anions are equal to 0. Now, considering that, we can move into our change row here. Since we have no products, our reaction is going to proceed forward to form our ion species. And that means we're going to consume hydrogen cyanide to form hydrogen cations and cyanide anions. So we're going to denote that change for hydrogen cyanide as minus X, and for hydrogen cations and cyanide anions as plus X. And then for our final row, our equilibrium row, this is going to be the initial concentration plus or minus the change, which gives us the equilibrium concentrations. Now we can use these to rewrite our equilibrium constant. Remember, for equilibrium constants, it's the concentration of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. And for this reaction, the equilibrium constant is equal to 4.9 times 10 to the negative 10. Now we can replace these concentrations with what we just figured out in our equilibrium row from our ICE table. That's going to give us X multiplied by X divided by 0.15 minus X, and that is equal to 4.9 times 10 to the negative 10. Now here, I want to revisit our discussion on the 5% approximation rule. I'm going to reiterate what I said earlier and then talk through whether we can make this approximation for this particular problem. This rule states that if the change in concentration X is less than 5% of the initial concentration, then X is negligible. This is often valid when K is very small or very large, or when the initial concentration is significantly high. Now, for this problem, this assumption is valid, and we can tell by looking at our value for the equilibrium constant and our initial concentration. There is a huge magnitude difference between these two values. So what we're going to do is we're going to apply the 5% approximation rule, and then after we solve this problem, we're going to validate whether that was a good decision or not, and I'll show you how to do that. In applying the 5% approximation rule, we get rid of this minus X, and now what we have is X squared divided by 0.15. That's equal to 4.9 times 10 to the negative 10. We can now begin to solve this by multiplying both sides by 0.15. That gets us X squared is equal to 0.15 multiplied by 4.9 times 10 to the negative 10. And then we're going to take the square root of both sides, and that's going to give us our value of X, which is equal to 8.6 times 10 to the negative 6. And we can go ahead and plug that back in for our equilibrium concentrations for our hydrogen cations and our cyanide anions. Now, how do we validate whether we use the 5% approximation rule appropriately? Was it correct that we used this 5% rule? To verify, we're just going to take our value of X that we calculated. We're going to divide it by our initial concentration of 0.15 and multiply by 100%. If we get a percentage that is less than 5, then we know we appropriately used our 5% approximation rule. And what you notice here is that this is much less than 5%. So once again, this approximation assumes that the change in concentration X is negligible. So we approximated 0.15 minus X to just 0.15. And this is valid if X is less than 5% of the initial concentration, which we just checked that it was. So we are all done with this problem. Now we can move into our next topic. Like we said earlier, the law of mass action defines the position of equilibrium, but achieving equilibrium takes time, which can vary from microseconds to millennia depending on the rates of the forward and reverse reactions. To gauge how far a reaction has progressed towards equilibrium, we can use the reaction quotient, denoted as Q. At any point during a reaction, we can measure the concentration of all the reactants and products and calculate Q using this equation. Now, this equation looks identical to the equation for the equilibrium constant, but the information it provides is different. While the equilibrium constant is calculated only at equilibrium, the reaction quotient can be calculated at any time. The concentrations used to calculate Q change over time as the reaction proceeds. So in short, the reaction quotient provides a snapshot of where the reaction is at a specific point in time, whereas the equilibrium constant describes the end state of the reaction. Now, comparing Q to K allows us to predict which direction the reaction will proceed to reach equilibrium. When the equilibrium constant is greater than the reaction quotient, then the forward reaction has not yet reached equilibrium. And that means that the reaction will proceed forward to reach equilibrium, converting more reactants to products. What about when Q equals K? Then the reaction is in dynamic equilibrium. The reactants and products are present in equilibrium proportions, and the forward and reverse rates of reaction are equal. Last, what if the reaction quotient is greater than the equilibrium constant? That means the forward reaction has exceeded equilibrium. The reaction will proceed in the reverse direction to reach equilibrium, converting products back to reactants. Now, following this discussion, it's important to understand how these concepts relate to Gibbs free energy and the direction of chemical reactions. This connection is going to help us predict whether a reaction will proceed spontaneously and in which direction it will move to reach equilibrium. Now, when the equilibrium constant is greater than the reaction quotient, then delta G is less than 0. The change in Gibbs free energy is negative, indicating that the forward reaction is spontaneous. The reaction will proceed in the forward direction to convert reactants into products until equilibrium is reached. What about when the reaction quotient and the equilibrium constant are equal? Delta G here is going to be 0, and this indicates a state of dynamic equilibrium where the forward and reverse reaction rates are equal. So there is no net change in the concentration of reactants and products. Last, when Q is greater than K, delta G is greater than 0. And this indicates that the forward reaction is non-spontaneous. The reaction will actually proceed in the reverse direction to convert the products back into reactants until equilibrium is reached. We see this relationship demonstrated in this figure right here. Now, a few points I also want to discuss before we move on to our next objective is the following. The concentration of pure solids and pure liquids, they do not appear in the equilibrium constant expression. So if you see liquid water at anywhere in the reaction, you do not include it in our equilibrium constant expression. So if you had, I don't know, hydrogen cyanide plus liquid water, all right, and this forms our products, when we write our equilibrium constant expression, we'll write the concentration of our products raised to their stoichiometric coefficients divided by the concentration of our reactants raised to their stoichiometric coefficients. You never include liquids or solids. In addition, the equilibrium constant, this is characteristic of a particular reaction at a given temperature. So in short, the equilibrium constant is temperature dependent. Now, the larger the value of the equilibrium constant, the farther to the right the equilibrium position. Now, to this, there's a couple of things that are going to make writing the equilibrium constant for reactions a little bit easier. For example, if you know that the equilibrium constant for a reaction is some value, the equilibrium constant for the reverse reaction is just going to be 1 over the equilibrium constant value. Then if the equation is multiplied by a factor m, all right, if we multiply this by a factor m, the original equilibrium constant must be raised to a power equal to that factor. So your new equilibrium constant is going to be k raised to that factor. And then finally, if the equations are added together, the overall equilibrium constant is going to be the product of the two original k values. So if you have a reaction A to B and C to D, and you add these equations together, each of them have an equilibrium constant, then your new equilibrium constant for A plus C gives you B plus D is going to be equal to K1 plus K2. So keep these 3 points in mind. I'm going to repeat them. If the equation is reversed, the new equilibrium constant is the reciprocal of the original one. If the equation is multiplied by a factor m, the original equilibrium constant must be raised to a power equal to that factor. And then finally, if the equations are added together, the overall equilibrium constant is going to be the product of the two original equilibrium constant values. Please keep these in mind as we move into our second objective, which we're going to cover in the next video. I hope that this has been helpful so far. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.